lesson 11.1, page 586, statistical measures of center and variation. In this lesson, you will learn how to compare the mean, median, and mode of a data set. You'll learn how to find the range and standard deviation of a data set, and you'll also learn how to identify the effects of transformations on data. First of all, we're going to talk about how we measure the center of data. A measure of center of data is a measure that represents the center or typical value of a data set. There are three ways we measure center of data. It's mean, and I think you know what mean is. Let's talk about it though just to make sure. The mean of data is the numerical value, which is the sum of the data divided by the data values. I'm just going to write it's the average, and you found average before, so the mean's the average. Okay? Now, one symbol that you need to be familiar with, I'm going to highlight it right here. That's the symbol for mean. It's read as X bar. So when you see the symbol X with a bar over it, like if I wrote this down on paper, that means the mean of the data is 15. So like if we took a chapter test, I'm making this up, and let's just pretend the chapter test was an 80. If I wrote on the board that, it means the average, the mean of the test was an 80. So that's what the symbol is. The median is another way to measure the center of data. And the median of a numerical data set is the middle number when the values are written in numerical order. So I know you found mean before. You arrange the numbers from lowest to highest and you pick the middle number. Now you got to be careful. When the data set has an even number of values, the median is the average of the two middle values. So I know you found median before. Okay? And then there's one other way to measure the center of data. It's called the mode. And what the mode is, it's the most common value in the data set. It's the value that occurs the most often. Now with mode, there may be more than one mode. There may be one, there could be none, and there could be more than one. Let's look at the sample problem, which goes through how we can find mean, median, and mode. It says, an amusement park hires students for the summer. The students' hourly wages are shown in the table. So I'm going to quickly just circle the table and highlight it. Here's the table of student wages. Okay, let's find the mean, and you can see what they're doing to find the mean. They're taking all 8 numbers, and I'm going to cross them off here, 1, 2, 3, 4, 5, 6, 7, 8. They're adding them all up. They're getting a total, and then they're taking that total and dividing by 8. So be careful when you put this in your calculator. You would have to put parentheses around what you're adding, and then divide that total by 8, and they're saying here the mean is 9.65. So my mean would be 9.65. So the average salary at the amusement park is $9.65, $9.65. Now to find the median, you notice what the book did. They took the numbers and they arranged them from least to greatest. And there's 8 numbers in the group. So to find the middle number, okay, take those out, take those out. My middle number's in between those two. So add those up, 17.4 divided by 2. The median is 8.7. Okay, so that's the median salary, $8.70. Now the mode, when I look at these numbers, do you notice the most common salary? I saw $8.25 twice. That's the mode. Okay, so there's 3 measures of center. The average was $9.65 for salary, the median was $8.70, and the mode was $8.25. Now, the median is best representing the data. The mode is the bottom amount. That's not a good measure of center, so even though the mode was $8.25, that doesn't really measure center very well. And the average, 965, if you look at this. There's only one person that makes more than $9.65. Everybody else makes less. So I don't know that that's a very good number to show the center amount of the values, okay? What I'd like you to do is pause the video. You try. Let's say the park hired another person for $8.45. I would like you to figure out how this affects the mean, median, and mode, and which measure of center would best represent the data. Pause the video and do that. Okay, and I'm back, and first of all, the mean of the data now, when I recalculate with this new salary in there, it's $9.52 is the mean. That's still not a good measure of center, because look, there's only one value that's above 952, so that's not a great measure of center. The median is now 865. That's right in the middle and half above. Half these salaries are above that, half below. That's a pretty good measure of center. The mode is 825 and 845. There's two sets of 825 and two sets of 845. Those aren't really a great measure of center either, because all the other salaries are bigger than that. So I'd say for part B, median is still the best measure of center for this data. Now, when you have data, you can have what's called an outlier. An outlier is a data value that is much greater or much smaller than the other values in the data set. Like if we go back to that previous problem, do you notice someone here was making $16.50 an hour at the amusement park? That's not close to these other ones. That would definitely be an outlier. And that's what they are asking here, okay? This value is much greater than the other wages. It's an outlier. So if we throw that value out and we recalculate this data without that in there. So I'm going to recalculate this data, and you can see the book's doing that here. Now we have a mean that's 867. Well, that mean is a lot better. Okay, when I look at it, I'm saying, wait a minute, there's three people that make more than that, and there's four that make less than that. That's much more accurate for a center of data. The new median of my data is now 865. See, and those are pretty close. The mode is still 825. So the mode is still not a great measure of center, even if we throw the outlier out. Outliers normally have a great effect on the mean. That's why when we talk about tests, like chapter tests, I never like talking about the mean, because if I have several people get 100, or I got 4 or 5 people getting a 10%, they can really throw off the mean because those are outliers of my normal data. Okay? Now they ask us, describe one possible explanation for the outlier. Well, these are all students working at the amusement park. Maybe this person was in charge of all of these other people. So this person could have been like a manager in a way, where these people just were the workers. So that would make sense. A manager should get more than the workers. All right, so that could be a possible reason why we had an outlier of that data. Now, they said in the book, maybe that person could have been a person that maintains a website while the other people just worked at the park. Okay, so again, it's open-ended. We don't know why. I would have said that person might have been a manager. Okay. What I'd like you to do is pause the video and try number 2. I want you to find the outlier of these salaries. Find how the outlier affects the mean, median, and mode, and then what's a possible explanation for the outlier. These are people at an auto repair service. So pause the video and do that. And I'm back, and so if I find the mean, median, and mode of all of these salaries, you can see that listed in black. But if I throw this outlier out, there's one person making $72,000. That's not close to the other people. If I throw the outlier out, then this is the data. And you notice how the mean dropped nearly $4,000, the median dropped $1,500, the mode didn't change. Okay, so how does the outlier affect the mean, median, and mode? Well, it dropped them all, and you notice these are much more closer now where they were significantly farther apart here. What is one possible explanation for the outlier? Again, if it's an auto parts store, that person making $72,000, maybe they manage the place and everybody else here just worked at the store. Okay. A measure of variation is a measure that describes the spread or distribution of the data set. One measure of variation is range. Range of a data set is the difference between the greatest value and the least value. So if I look at show A and I want to find the range, what I can do is I find the high value in the group. The highest value here I see is 30, and the lowest is 19. Timeout, the highest value is 31. I missed 31. High value 31, low value 19. If I do 31 minus 19, I just got the range. The range is 12 years for show A. For show B, let's find my range. The highest age of the group looks to be 48, and the lowest is 19. 48 minus 19, there's a range of 29 years here. Okay, this is showing the spread of my data or distribution of the data. Range is a way of showing spread or distribution of the data. A disadvantage of using the range to describe the spread of data is that the range only uses two data values. It only uses the high and low amount. A measure of variation that uses all the data values is called standard deviation. Now, the standard deviation of a numerical set of data is how much a typical value differs from the mean. That's standard deviation. How much does a typical value differ from the mean? There's a symbol for standard deviation. It's called sigma. The symbol looks like an O with a little kind of tail off the end. That's sigma. Okay? So when you do standard deviation, a small standard deviation means the data are clustered around the mean. But if you have a large standard deviation, that means the data are more spread out. So if I had a chapter test and the average was 75, and I found that my standard deviation was 5, that means that typically, okay, again, typically, most of my students had a score of 75, or they were only 5 points off from that score either way. So like a lot of kids had a 70 to 80 is what that would mean. But if I have an average of 75 and I had a standard deviation of 25, that means my data is way more, my student scores were way all over the place because I had a group of people that would score anywhere from as high as 100, 25 more than 75, or as low as 50. Okay? Typically, standard deviation, 2/3 of the group scores within the standard deviation. Okay, 2/3 of the group. Now, to find standard deviation, we don't have to worry about the formula. We're going to use your calculator. So I would get your calculator out. We're going to type this data in our calculator. These were the ages of people in show A. We're going to find the standard deviation for show A. So take your calculator out. Let's do that together. And you'll notice on my calculator I cleared the RAM. And what I'm going to do is hit, you've done this before, hit the stat key, press edit, and now I need you to type in those ages. I'm going to pause the video and do that. Okay, so you can see I've typed these in. I'm just scrolling so you can see them all. Now, one way you can double check to make sure that you have the right amount of data in. Okay? You notice show A has 12 ages. So if you look carefully at the screen right now, I'm going to highlight You notice how there's a little 12 here. The entry 31 years old is the 12th entry of my group. It's matching. There's 12 ages. So you can use that to double check. Hey, did I enter all this in right? Okay, now from there it's easy. Hit stat, arrow once to calc, and you want to do one variable stat, so option 1. And then on the newer calculators, you'll have to scroll down to calculate. I have an older calculator. Just press enter on mine, and now look at all this data. Now this is why the symbols are important, okay? So first of all, do you see this gave me the mean? The mean is 25. So the average age of show A is 25. And then, do you notice the sigma symbol? I'm circling it. There's the sigma symbol. So typically, our contestants are about 4.2 years off from age 25. So in other words, the average is 25, but most of our contestants are within 4.2 years of 25. So in other words, 21 through 29 years old is the range. I shouldn't say the range. Typically, 2/3 of that show has students or kids that are ages 21 to 29 years old. Okay, that's what this 4.2 standard deviation is telling me. A couple other things I can see on here. If I scroll down, this will show me the minimum value. The lowest age was 19. The median age was 26 of show A, and the max age was 31. So you can get all this data by just using the stat key, typing it in, and then doing stat, calc, option 1, enter. And it'll give you the standard deviation. We don't have to remember the formula. What I would like you to do is I want you now to find the standard deviation of show B, okay? You can use your calculator to do that, and then I want you to compare the standard deviations for show A and B. What can you conclude? Use your calculator, pause the video, and do that. And I'm back. When I did show B, I found out that the standard deviation was about 7.5 years. So the typical age of contestants in show B is definitely greater than show A, okay? Show B differs by about 7.5 years from the average. And then compare the standard deviations for both shows. What can you conclude? Overall, show A's contestants, remember show A had a standard deviation of 4.2. Show A's contestants are closer to the same age as a whole versus show B. Show B, the ages were much more spread. And to wrap up the video, we're going to quickly talk about effects of data transformations. A data transformation is a procedure that uses a mathematical operation to change a data set into a different data set. So let's talk about data transformations using addition. When a real number k is added to each value in a numeric data set, two things will happen. The measures of the data, the measures of center, I should say, of the new data can be found by adding k to the original measures of center. And the measures of variation, however, will stay the same. Okay? The standard deviation won't change. They'll still deviate the same from the mean. Now, if you're reading that, you're like, what the heck is he talking about? What do they mean? Well, let's go to that auto parts example. And you can still see all the data from the original calculation. I'm circling it here. Let's pretend that we decided that we're going to add $10,000 to every salary of the data. So my real number k is 10,000. So what's that going to do? Well, all I have to do is go up here. It's going to change my mean by 10,000. So I'd add 10,000, make it 52,875. It would make my median 10,000 higher, which would now become 49,500. And it would make my mode 10,000 higher, 48,000 would be my new mode. I don't have to add 10,000 to all these salaries and recalculate all this out. Now, it will not change my range, okay? my new top salary is 82 and my low salary is 42. If I take the top and bottom and subtract, I'm still going to get a $40,000 range. Okay, so the range won't change, but the mean, median, and mode will change. So that's what this is trying to tell me. If I add a certain amount or subtract a certain amount to my data set, my mode, my mean, and my median will just change by that same amount. However, my range or my standard deviation won't change. If I multiply, that will double, I shouldn't say double, that will change the measure of center and variation. So the reason I said double, I was going to use that for my example. Let's pretend that I'm going to go to the auto parts sample and I'm going to double this time. My K value, I'm going to multiply everything by 2. So I'm going to double all the salaries is what I'm saying. I'll put times 2. Well, that's going to double my mean. So instead of 42,875, it's going to be double that, which would be 85,650, I think. I'm doing it off the top of my head. My median will double. That would turn into 79,000. And my mode would double to 76,000. And remember how I said my range here was 40,000? My range would also double. My new range would be 80,000. So that's what that is trying to tell me here. I don't have to double every individual amount and then recalculate it all. So this is basically saying there is a shortcut to transforming your data. You don't have to recalculate the whole thing from scratch. I'm going to pause the video here. If you have any questions, make sure you ask in class.